Electron microscope, Wikipedia audio. An electron microscope is a microscope that uses a beam of accelerated electrons as a source of illumination. As the wavelength of an electron can be up to 100,000 times shorter than that of visible light photons, electron microscopes have a higher resolving power than light microscopes and can reveal the structure of smaller objects. A scanning transmission electron microscope has achieved better than 50 pm resolution in annular dark field imaging mode and magnifications of up to about 10,000,000x, whereas most light microscopes are limited by diffraction to about 200 nm resolution and useful magnifications below 2000x. Electron microscopes have electron optical lens systems that are analogous to the glass lenses of an optical light microscope. Electron microscopes are used to investigate the ultrastructure of a wide range of biological and inorganic specimens, including microorganisms, cells, large molecules, biopsy samples, metals, and crystals. Industrially, electron microscopes are often used for quality control and failure analysis. Modern electron microscopes produce electron micrographs using specialized digital cameras and frame grabbers to capture the image. History. The first electromagnetic lens was developed in 1931 by Hans Busch. According to Dennis Gaber, the physicist Leo Szilard tried in 1928 to convince him to build an electron microscope, for which he had filed a patent. Chemical fixation for biological specimens aims to stabilize the specimen's mobile macromolecular structure by chemical cross-linking of proteins with aldehydes such as formaldehyde and glutaraldehyde, and lipids with osmium tetroxide. Negative stain suspensions containing nanoparticles or fine biological material are briefly mixed with a dilute solution of an electron-opaque solution such as ammonium molybdate, uranyl acetate, or phosphotungstic acid. This mixture is applied to a suitably coated M-grid, blotted, then allowed to dry. Viewing of this preparation in the TEM should be carried out without delay for best results. The method is important in microbiology for fast but crude morphological identification, but can also be used as the basis for high-resolution 3D reconstruction using M-tomography methodology when carbon films are used for support. Negative staining is also used for observation of nanoparticles, cryo fixation, freezing a specimen so rapidly, in liquid ethane, and maintained at liquid nitrogen or even liquid helium temperatures, so that the water forms vitreous ice. This preserves the specimen in a snapshot of its solution state. An entire field called cryo-electron microscopy has branched from this technique. With the development of cryo-electron microscopy of vitreous sections, it is now possible to observe samples from virtually any biological specimen close to its native state, dehydration or replacement of water with organic solvents such as ethanol or acetone, followed by critical point drying or infiltration with embedding resins. Also freeze drying, embedding, biological specimens after dehydration. Tissue for observation in the transmission electron microscope is embedded so it can be sectioned ready for viewing. To do this, the tissue is passed through a transition solvent such as propylene oxide or acetone and then infiltrated with an epoxy resin such as araldite, EPON, or Durcupan. Tissues may also be embedded directly in water-miscible acrylic resin. After the resin has been polymerized, the sample is thin-sectioned and stained. It is then ready for viewing. Embedding materials. After embedding in resin, the specimen is usually ground and polished to a mirror-like finish using ultrafine abrasives. The polishing process must be performed carefully to minimize scratches and other polishing artifacts that reduce image quality. Metal shadowing: metal is evaporated from an overhead electrode and applied to the surface of a biological sample at an angle. The surface topography results in variations in the thickness of the metal that are seen as variations in brightness and contrast in the electron microscope image. Replication: a surface shadowed with metal at an angle is coated with pure carbon evaporated from carbon electrodes at right angles to the surface. This is followed by removal of the specimen material to produce a surface replica that records the surface ultrastructure and can be examined using transmission electron microscopy. Sectioning produces thin slices of specimen, semi-transparent to electrons. These can be cut on an ultramicrotome with a diamond knife to produce ultra-thin sections about 60–90 nm thick. Disposable glass knives are also used because they can be made in the lab and are much cheaper. Staining uses heavy metals such as lead, uranium, or tungsten to scatter imaging electrons and thus give contrast between different structures, since many materials are nearly transparent to electrons. In biology, specimens can be stained en bloc before embedding and also later after sectioning. Typically, thin sections are stained for several minutes with an aqueous or alcoholic solution of uranyl acetate followed by aqueous lead citrate. Freeze fracture or freeze etch, a preparation method particularly useful for examining lipid membranes and their incorporated proteins in face on view. The fresh tissue or cell suspension is frozen rapidly, then fractured by breaking or by using a microtome while maintained at liquid nitrogen temperature. The cold fractured surface is then shadowed with evaporated platinum or gold at an average angle of 45 degrees in a high vacuum evaporator. A second coat of carbon, evaporated perpendicular to the average surface plane, is often performed to improve stability of the replica coating. The specimen is returned to room temperature and pressure, then the extremely fragile pre-shadowed metal replica of the fracture surface is released from the underlying biological material by careful chemical digestion with acids, hypochlorite solution, or SDS detergent. The still floating replica is thoroughly washed free from residual chemicals, carefully fished up on fine grids, dried, then viewed in the TEM. Freeze fracture replica immunogold labeling. The freeze fracture method has been modified to allow the identification of the components of the fracture face by immunogold labeling. Instead of removing all the underlying tissue of the thawed replica as the final step before viewing in the microscope, the tissue thickness is minimized during or after the fracture process. The thin layer of tissue remains bound to the metal replicas so it can be immunogold labeled with antibodies to the structures of choice. The thin layer of the original specimen on the replica with gold attached allows the identification of structures in the fracture plane. There are also related methods which label the surface of etched cells and other replica labeling variations. Ion beam milling thins samples until they are transparent to electrons by firing ions at the surface from an angle and sputtering material from the surface. A subclass of this is focused ion beam milling, where gallium ions are used to produce an electron transparent membrane in a specific region of the sample, for example through a device within a microprocessor. Ion beam milling may also be used for cross-section polishing prior to SEM analysis of materials that are difficult to prepare using mechanical polishing, conductive coating and ultra-thin coating of electrically conducting material, deposited either by high vacuum evaporation or by low vacuum sputter coating of the sample. This is done to prevent the accumulation of static electric fields at the specimen due to the electron irradiation required during imaging. The coating materials include gold, gold/palladium, platinum, tungsten, graphite, etc., Earthing to avoid electrical charge accumulation on a conductive coated sample, it is usually electrically connected to the metal sample holder. Often an electrically conductive adhesive is used for this purpose. The physicist Ernst Ruska and the electrical engineer Max Knoll constructed the prototype electron microscope in 1931, capable of 400 power magnification. The apparatus was the first demonstration of the principles of electron microscopy. 2 years later, in 1933, Ruska built an electron microscope that exceeded the resolution attainable with an optical microscope. Moreover, Reinhold Rudenberg, the scientific director of Siemens Schuckertwerke, obtained the patent for the electron microscope in May 1931. In 1932, Ernst Lubke of Siemens and Halske built and obtained images from a prototype electron microscope, applying concepts described in the Rudenberg patent applications. 5 years later, the firm financed the work of Ernst Ruska and Bodo von Borries, and employed Helmut Ruska to develop applications for the microscope, especially with biological specimens. Also in 1937, Manfred von Ardenne pioneered the scanning electron microscope. The first commercial electron microscope was produced in 1938 by Siemens. The first North American electron microscope was constructed in 1938, at the University of Toronto, by Eli Franklin Burton and students Cecil Hall, James Hillier, and Albert Priebus, and Siemens produced a transmission electron microscope in 1939. Although contemporary transmission electron microscopes are capable of 2 million power magnification, as scientific instruments, they remain based upon Ruska's prototype. The original form of electron microscope, the transmission electron microscope, uses a high-voltage electron beam to illuminate the specimen and create an image. The electron beam is produced by an electron gun, commonly fitted with a tungsten filament cathode as the electron source. The electron beam is accelerated by an anode typically at plus 100 keV with respect to the cathode, focused by electrostatic and electromagnetic lenses, and transmitted through the specimen that is in part transparent to electrons and in part scatters them out of the beam. When it emerges from the specimen, the electron beam carries information about the structure of the specimen that is magnified by the objective lens system of the microscope. The spatial variation in this information may be viewed by projecting the magnified electron image onto a fluorescent viewing screen coated with a phosphor or scintillator material such as zinc sulfide. Alternatively, the image can be photographically recorded by exposing a photographic film or plate directly to the electron beam, or a high-resolution phosphor may be coupled by means of a lens optical system or a fiber optic light guide to the sensor of a digital camera. The image detected by the digital camera may be displayed on a monitor or computer. The resolution of TEMS is limited primarily by spherical aberration, but a new generation of aberration correctors have been able to partially overcome spherical aberration to increase resolution. Hardware correction of spherical aberration for the high-resolution transmission electron microscopy has allowed the production of images with resolution below 0.5 angstrom and magnifications above 50 million times. The ability to determine the positions of atoms within materials has made the HIRTEM an important tool for nanotechnologies research and development. Transmission electron microscopes are often used in electron diffraction mode. The advantages of electron diffraction over X-ray crystallography are that the specimen need not be a single crystal or even a polycrystalline powder, and also that the Fourier transform reconstruction of the object's magnified structure occurs physically and thus avoids the need for solving the phase problem faced by the X-ray crystallographers after obtaining their X-ray diffraction patterns of a single crystal or polycrystalline powder. Cryobiology, cryo-electron microscopy, diagnostic electron microscopy, drug research, electron tomography, particle analysis, particle detection, protein localization, structural biology, tissue imaging, toxicology, virology. One major disadvantage of the transmission electron microscope is the need for extremely thin sections of the specimens, typically about 100 nanometers. Creating these thin sections for biological and materials specimens is technically very challenging. Semiconductor thin sections can be made using a focused ion beam. Biological tissue specimens are chemically fixed, dehydrated and embedded in a polymer resin to stabilize them sufficiently to allow ultra-thin sectioning. Sections of biological specimens, organic polymers, and similar materials may require staining with heavy atom labels in order to achieve the required image contrast. The SEM produces images by probing the specimen with a focused electron beam that is scanned across a rectangular area of the specimen. When the electron beam interacts with the specimen, it loses energy by a variety of mechanisms. The lost energy is converted into alternative forms such as heat, emission of low-energy secondary electrons and high-energy backscattered electrons, light emission or X-ray emission, all of which provide signals carrying information about the properties of the specimen surface, such as its topography and composition. The image displayed by an SEM maps the varying intensity of any of these signals into the image in a position corresponding to the position of the beam on the specimen when the signal was generated. In the SEM image of an ant shown below and to the right, the image was constructed from signals produced by a secondary electron detector, the normal or conventional imaging mode in most SEMs. Types. Generally, the image resolution of an SEM is lower than that of a TEM. However, because the SEM images the surface of a sample rather than its interior, the electrons do not have to travel through the sample. This reduces the need for extensive sample preparation to thin the specimen to electron transparency. The SEM is able to image bulk samples that can fit on its stage and still be maneuvered, including a height less than the working distance being used, often 4 mm for high-resolution images. The SEM also has a great depth of field, and so can produce images that are good representations of the three-dimensional surface shape of the sample. Another advantage of SEMs comes with environmental scanning electron microscopes that can produce images of good quality and resolution with hydrated samples or in low, rather than high, vacuum or under-chamber gases. This facilitates imaging unfixed biological samples that are unstable in the high vacuum of conventional electron microscopes. In their most common configurations, electron microscopes produce images with a single brightness value per pixel, with the results usually rendered in grayscale. However, often these images are then colorized through the use of feature detection software, or simply by hand editing using a graphics editor. This may be done to clarify structure or for aesthetic effect and generally does not add new information about the specimen. In some configurations, information about several specimen properties is gathered per pixel, usually by the use of multiple detectors. In SEM, the attributes of topography and material contrast can be obtained by a pair of backscattered electron detectors, and such attributes can be superimposed in a single color image by assigning a different primary color to each attribute. Similarly, a combination of backscattered and secondary electron signals can be assigned to different colors and superimposed on a single color micrograph displaying simultaneously the properties of the specimen. Some types of detectors used in SEM have analytical capabilities, and can provide several items of data at each pixel. Examples are the energy dispersive X-ray spectroscopy detectors used in elemental analysis and cathodoluminescence microscope systems that analyze the intensity and spectrum of electron-induced luminescence in geological specimens. In SEM systems using these detectors, it is common to color-code the signals and superimpose them in a single color image, so that differences in the distribution of the various components of the specimen can be seen clearly and compared. Optionally, the standard secondary electron image can be merged with the one or more compositional channels, so that the specimen's structure and composition can be compared. Such images can be made while maintaining the full integrity of the original signal, which is not modified in any way. In the reflection electron microscope, as in the TEM, an electron beam is incident on a surface, but instead of using the transmission or secondary electrons, the reflected beam of elastically scattered electrons is detected. This technique is typically coupled with reflection high-energy electron diffraction and reflection high-energy loss spectroscopy. Another variation is spin-polarized low-energy electron microscopy, which is used for looking at the microstructure of magnetic domains. The STEM rasters a focused incident probe across a specimen that has been thinned to facilitate detection of electrons scattered through the specimen. The high resolution of the TEM is thus possible in STEM. The focusing action occurs before the electrons hit the specimen in the STEM, but afterward in the TEM. The STEM's use of SEM-like beam rastering simplifies annular dark field imaging, and other analytical techniques, but also means that image data is acquired in serial rather than in parallel fashion. Often TEM can be equipped with the scanning option, and then it can function both as TEM and STEM. Materials to be viewed under an electron microscope may require processing to produce a suitable sample. The technique required varies depending on the specimen and the analysis required. Transmission electron microscope. Scanning electron microscope. Electron microscopes are expensive to build and maintain, but the capital and running costs of confocal light microscope systems now overlaps with those of basic electron microscopes. Microscopes designed to achieve high resolutions must be housed in stable buildings with special services such as magnetic field cancelling systems. Color. Reflection electron microscope. Scanning transmission electron microscope. Sample preparation. Disadvantages. The samples largely have to be viewed in vacuum, as the molecules that make up air would scatter the electrons. An exception is liquid phase electron microscopy using either a closed liquid cell or an environmental chamber, for example, in the environmental scanning electron microscope, which allows hydrated samples to be viewed in a low-pressure wet environment. Various techniques for in situ electron microscopy of gaseous samples have been developed as well. Scanning electron microscopes operating in conventional high vacuum mode usually image conductive specimens, therefore non-conductive materials require conductive coating. The low-voltage mode of modern microscopes makes possible the observation of non-conductive specimens without coating. Non-conductive materials can be imaged also by a variable pressure scanning electron microscope. Small, stable specimens such as carbon nanotubes, diatom frustules and small mineral crystals require no special treatment before being examined in the electron microscope. Samples of hydrated materials, including almost all biological specimens, have to be prepared in various ways to stabilize them, reduce their thickness and increase their electron optical contrast. These processes may result in artifacts, but these can usually be identified by comparing the results obtained by using radically different specimen preparation methods. Since the 1980s, analysis of cryo-fixed, vitrified specimens has also become increasingly used by scientists, further confirming the validity of this technique. Applications: Biology and life sciences. General. History 2. Other.